Hey everybody, welcome back. It's time to start chapter 2. We're going to break up this chapter into two approximately 1-hour videos. There's a lot in this chapter. The first part is going to be setting up the skills that we need to do the problems in the second part. So again, first part, we're building our skills. The second part, we're going to take those skills from part 1 and do some problems. This chapter is dealing with chemistry and measurements. So in this image, you have someone taking a measurement. So we're taking a pulse, we've got blood pressure. Those are all different types of measurements that you take in medicine, plenty more that you can think of. We're going to be talking about some of the units that we use for different measurements in chemistry. For the first section, we'll talk about the names and abbreviations for metric and SI units that we use to measure volume, length, mass, temperature, and time. Oftentimes you'll see the metric system in use when we're dealing with measurements. There's also the International System of Units, which is the SI units. So there are some similarities, and for some measurements, they use the same exact units, but there are a few differences that we'll go over. So this table will be really handy for you. It's got the measurement, volume, length, etc., metric, and SI. Each of these is different, so they mean the same thing. For example, liter in the metric system, cubic meter in SI. We're using, it's the same thing, okay? There's the meter for both the metric system and SI. Gram versus kilogram. So it's very similar, right? One notable difference, though, is the degrees Celsius versus Kelvin. Kelvin is an absolute temperature scale, and we'll talk about that in a second. And time, we use seconds for both. So you need to know the differences between these two. You need to look at a unit of measure and see and know whether or not it's metric or SI. We'll start with volume. You'll usually see volume in liters and milliliters, particularly when you're doing chemistry. Volume is the space occupied by a substance. Again, the SI unit is the cubic meter, but in the metric system, we use a liter. Okay. Graduated cylinders, which is what's pictured over here. It's a graduated cylinder. Oftentimes you're going to use one of those in chemistry class just to measure small volumes. For length, we use the meter and the centimeter. Both the metric and SI use the meter. Okay. It's a little bit longer than a yard. For mass, the metric units, we use gram, SI units, kilogram. They're related. You see gram in both of the names, and shortly you're going to see how they're related. But when you're looking at the mass of an object, you're measuring the quantity of material that it contains. Again, in SI, you're going to express that in kilograms. Metric system, you're probably going to stick with grams. Temperature, we've got degrees Celsius and Kelvin. Degrees Celsius is what we typically use in the metric system. Kelvin is for SI. That doesn't mean that we can't use the Kelvin scale. It's not really a scale, it's an absolute scale, okay? But oftentimes you'll see degrees Celsius. Okay. Now the difference between Celsius and Kelvin is that Kelvin is an absolute scale. So when it's 0 Kelvin, it means really 0. Whereas with degrees Celsius, you can have 0 degrees Celsius, you can have -2 degrees Celsius, right? 0 isn't really 0. There's something less than 0. With Kelvin, 0 Kelvin means there is no heat in the system, absolute 0. Okay. We'll be using the Kelvin scale in chapter 8 when we do gas laws. So this will come back around. time, we use seconds. There are plenty of other units of time that you're obviously familiar with because you've been living for this long on Earth. Years, days, hours, all those things. But the metric and SI unit of time is the second. Now you can quiz yourself here. What are the SI units for the following versus the metric? You can also do the metric units. Make sure that you know it. But all of the answers for this question are in this table. I'm not going to take the time to go through and write out each one. You can see it right here. The second section, we're going to cover measured numbers and significant figures. Measured numbers are numbers that you obtain when you measure a quantity. Okay? An example would be height, weight, temperature. So a height would be a length, the weight would be a mass. All of these numbers are measured numbers. We get them from some kind of an instrument. To write down a measured number, you have to observe the numerical values on the marked lines. So if you think about a ruler, it's going to be a better rectangle than that, but bear with me. Let's say this is our ruler. And we're measuring in centimeters. You're going to take whatever it is that you need to measure. Let's say you're measuring this red line. Estimate the length of this line. Well, we know that it's going to be somewhere between 3 and 4 centimeters, right? So we're observing the numerical values on the marked lines. There's a 3 here, there's a 4 here. Our line is somewhere in between. Now we need to estimate the value of the number between the marks. It looks like it's a little bit more than halfway, so maybe it's 3.6 centimeters. This number, the 0.6, we estimated that number. And you'll notice it is the final number in our measured number. Each measured number has an estimated number. If you were to use a graduated cylinder, and let's say that each tick mark is 10 milliliters. We pour some water in. And we need to estimate what this is. We know it's between 20 and 30. So that's 20. Now we can estimate where we are. I would say that this is almost 25, maybe 24. Now, depending on your book, depending on what other chemistry classes you might take and what textbook you use, you'll either write 24 milliliters or 24.0. For your book, we estimated the 4, so that should be the final digit, the 24 milliliters. But if you look at other textbooks, other chemistry textbooks, or things online, you may see this bottom answer, 24.0. I just don't want you to get confused if you see that and then you're like, but wait, why isn't this the answer? There's a little bit of there's slight differences in how people represent significant figures, which we're going to talk about in just a little bit here. But for your book, and when you're doing your homework, make sure that you represent it with the number that you observe and the number you estimate. And the estimated number is the final number in your measurement. So here we've got some lengths of different objects for A, B, and C. We've got a wooden stick that we're measuring the number of centimeters its length is. Notice how in A we have 1 decimal place, right? 4.5. That 0.5 is estimated. This is the same concept we were talking about before. Their pictures are just a little bit prettier. In B, we have more than just the 4 and the 5, but we've also got tick marks in between. Each of those little tick marks is 1 millimeter. So now we can actually estimate between these smaller tick marks. It's very difficult to mark here. So now we can mark in between those 2 tick marks, and now we have 2 decimal places, the tenths and the hundredths. Notice in C, we have a number in the tenths place because we could estimate it, right? We're not going to say just 3 centimeters with no 0.0, because what we're saying is we're estimating this tenths place, and the estimation is that it's 0. So it is exactly 3 centimeters. But we're representing the fact that we could get more information from this ruler. So all these numbers and all the digits in a measured number, they're significant figures, including the estimated digit. And we use significant figures to represent the amount of error associated with the measurement. All of the non-zero digits and the zeros between digits are significant. So non-zero digits would be 1, 2, 3, 4, etc., right? And zeros between digits, well, let's say that you had a number 108. There would be 3 significant figures in that number. And I abbreviate significant figures SF or sig figs. So you'll hear me say sig figs, you'll hear me say significant figures, and I'll write both sig figs and SF. Not trying to confuse you, but they all mean significant figures. Now we have to be careful with significant figures because the zeros can be a little tricky. Significant figures are not zeros that act as placeholders before digits. So an example of that would be if your number was 0.11 millimeters, this 0 is a placeholder. Likewise, if we had another 0.011, both of these zeros are placeholders. It's just to show what the actual number is, not really measured. However, significant figures are zeros at the end of a decimal number. 1.0 has 2 sig figs. However, 10 has 1 sig fig because there's no decimal. And we'll do plenty of practice with this as well. And this table has some examples, just like I went through and gave you some examples of numbers and measurements. This table gives you examples of each of the rules for significant figures. And when you're doing your homework, you can compare, okay, I have this kind of a situation. Is this significant or not significant? That will help you a lot when you're doing your homework. It'll also help you in class. So if you want to have this table on hand when we're going through practice problems, wouldn't be a bad idea. The tables are very helpful in this book. So we covered measured numbers, right? We're taking a height, a weight, some kind of measurement using an instrument. And all those digits that we record are significant. There are also exact numbers. Exact numbers are not measured, and therefore, we don't worry about significant figures. When we're using measurements to do calculations, we don't use the exact numbers to determine the number of significant figures to report it an answer. That'll become a little more clear in the second part of the Chapter 2 lecture when we're doing problems. Exact numbers are obtained by counting. So 8 cookies, 6 eggs, these are things that you can count. You can look and say, I have this many. Exact numbers are also definitions that compare two units. So for example, if we have 1 quart, it's the same thing as saying 4 cups. So that's a definition that compares two things. Exact numbers are also definitions in the same measuring system, and we're going to get to this very shortly. 1 kilogram is the same as 1,000 grams. Those are exact numbers. This table has some examples of exact numbers, counted numbers, and defined equalities. We're going to talk about what an equality is in this lecture. But these are examples. When you're doing your homework, again, compare the questions you're being asked to the examples that are given in the tables, and that will help you a lot. Here's a learning check. I encourage you to pause and try this on your own. If you don't, that's okay. We'll do practice in class. Identify the numbers below as measured or exact. Give the number of significant figures in each measured number. So A, 3 coins. That is exact. It's something that you can count. The diameter of a circle is 7.902 centimeters. That's a measurement. One of the clues, centimeters. That's a length. And since we have a measurement, we need to give the number of significant figures in this measured number. There are 4 significant figures: the 7, the 9, the 0, and the 2. Remember, zeros that are sandwiched between 2 non-zero digits are always going to be significant. Part C, 60 minutes is equal to 1 hour. That's exact. Okay, this is a definition. It's a definition of two quantities. 60 minutes is equal to 1 hour. They're the same thing, just different units. Hopefully you did well on that one if you paused it. If you didn't, we'll practice some more in the live lecture. More on significant zeros and scientific notation. Remember, we did scientific notation in Chapter 1. When you have zeros that are significant in a really large number, it's best to use scientific notation. That way you can show which zeros are significant and which ones aren't, and you don't have to write out a bunch of zeros. That's always a plus, right? In this textbook, they will place a decimal point after a significant zero at the end of a number. So here's the example that's given. If only the first zero in 300 meters is significant, but the second one isn't, it will be written in scientific notation. So to write that out again, 3.0 times 10 to the second meters has 2 sig figs. But what if the book is going to represent that all of the zeros, both of them, are significant? Then there will be a decimal point at the end. And that would be 3 significant figures with the decimal point. So make sure that you pay attention to your numbers, particularly when there are decimals involved. The decimals and the zeros can be a little bit tricky, but if you pay attention and you check your work, you'll be fine. Still talking about zeros and scientific notation. Again, those zeros can be really tricky, so make sure that you practice, and when you're doing your homework, your quiz, and your exam, pay attention, take your time, check your work. Zeros at the end of a large standard number without a decimal point are not significant. So we said that before. If we had that 300 meters, that's only one significant figure. 400,000 grams, that's only one significant figure, just the 4. If we were to write that in scientific notation, it would just be 4 times 10 to the 5th grams. There's no decimal point, there's no other zeros after the 4. With 850,000, we've got 2 significant figures, the 8 and the 5. And so that's how you would write it in scientific notation, 8.5 times 10 to the 5th. All those other zeros, they're just placeholders. Zeros at the beginning of a decimal number are also placeholders, and they're not significant. So 0.0004 still only has one sig fig, and you'd represent that as 4 times 10 to the minus 4. Again, we'll do practice. Sometimes it takes practice to really cement it into your brain versus just seeing it and writing it down in your notebook. So if it's still a little fuzzy, that's okay. Here's a learning check that I encourage you to do. If you don't feel comfortable doing it, if you feel like, I don't really think that I understand it well enough, that's fine, just keep watching. But make sure that by the end of the live lecture, you're in a place where you can attempt problems on your own and be at least marginally confident that you understand what you're doing, or if you get it wrong, you see what your mistake was if someone points it out. So here we've got to identify significant and non-significant zeros in each of these numbers and write them in the correct scientific notation. So here's what I'm going to do. All of the non-significant zeros, I'm going to circle. So in part A, we've got a decimal number. All of these zeros are non-significant. So when we write this in scientific notation, notice I included this last 0 because that one is significant. That's how we would write that number. So this 0 is significant. In B, all of these digits are significant. That 0 is sandwiched between 2 non-zero digits. When we write this in scientific notation, we have to use all those digits. In C, these last 3 zeros are non-significant. They're just placeholders. 1.044 is our coefficient. So remember, let's do a quick refresh. You've got your coefficient and your power of 10. The coefficient has to be at least 1 but less than 10. And then the power of 10, the n here, tells you how many decimal places you've moved. A negative n means that the standard number that you're converting is less than 1. A positive n, which you don't usually see the positive sign, means that your standard number is more. Well, it's actually equal to or greater than 1. Let's write it correctly. Greater than or equal to 1. Okay, back to our regularly scheduled programming. We've got our coefficient for C, 1.044. And if we put that decimal point there, then we need to count 1, 2, 3, 4, 5, 6. 10 to the 6 liters. Don't forget to put units for all of these, because all of these are measurements. Measurements have units. Without the units, we don't know what it's measuring. Okay. Moving right along. Significant figures in calculations. So we're not just going to have measurements and then that's the end. We're using these measurements and doing calculations. And there are certain rules for adding, subtracting, multiplying, and dividing with sig figs. First, we're going to cover rounding. Now, you've probably covered rounding before, but just to make sure everyone is on the same page, we're going to do it here too. The rules for rounding. If the first digit to be dropped is 4 or less, then that digit and everything else is dropped. If the first digit to be dropped is 5 or greater, then the last retained digit is increased by 1. Let's just do some examples. We've got 3 numbers here that we're going to round off to 3 significant figures and 2 significant figures. I'll do 3 sig figs in black and 2 sig figs in purple. Let's first fill in the 3 sig figs. And feel free to pause it and do it and make sure that you're good. And if you are, thumbs up. So 3 significant figures means the 2 is going to be our last retained digit. We're looking at the 3 to see whether or not we round up or we stay the same. Next to the 2 is a 3. 3 is 4 or less, so the 3 and everything else is going to be dropped off. We're left with 8.42. Second number, 14.780. 3 sig figs. That means we're looking at the 7. That's our last retained digit. Next to it, there's an 8. 8 is 5 or greater, so we're going to increase that 7 to an 8. And our rounded number is 14.8. 3,256. 3 sig figs means the 5. The number next to it is a 6, which is 5 or greater. So we're going to bump that 5 up to a 6. 3, 2, 6. Watch this. Add a 0. Why? Because we need to hold the place of that 6. 326 is not the same as 3,260. So we have to replace that 6 in this number with a 0. Okay? That's called adding a placeholder 0. If you were promised $3,260 and instead you were given 326, you would be mad. Remember that when you're rounding and debating those placeholder zeros. Now we'll go back through with the same numbers, only this time we'll round to 2 significant figures. For the first number, it means that we're going to retain the 4 and everything else after that has to go. 2 is 4 or less, so we're just going to write 8.4. 14.780, we're looking at retaining the 4 as our last digit. Next to that is a 7. That means we're going to bump that 4 up to a 5 and write 15. Last one, 3,256. We're looking at the 2 as our last retained digit. That means we're looking at the 5 to tell whether or not we round up or stay the same. 5 is 5 or greater, so we're going to bump that 2 up to a 3. And 33 is not the same as 3,300. We've got to add placeholder zeros. We'll do some practice on this, especially with the adding placeholder zeros. That is typically an area that we need to do more practice than others. So if you still feel a little bit confused about what placeholder zeros are and when to add them, you're not alone. We'll cover it in class even more, and then you'll be a pro. Let's do some multiplication and division. The final answer that you report has to have the same number of sig figs as the measurement with the fewest significant figures. So in our example, we've got 2 lengths, 24.66 centimeters and 0.35 centimeters. 24.66 has 4 sig figs. 0.35 only has 2. Our answer must have 2 sig figs because the measurement in our problem with the fewest significant figures is the 0.35 centimeters, which is only 2. So when you're doing a problem and you're multiplying or dividing, figure out how many sig figs are in each of the measurements, ignore the exact numbers, and determine how many sig figs your answer must have. It has the same number of sig figs as the measurement with the fewest significant figures. It's one of those things that you just have to practice. So here's another example. Here we're multiplying and dividing. Let's look at all of our measurements. 21.5, that's 3 significant figures. 0.30 centimeters, that's 2. And 1.88, that's another 3. When you put that in your calculator, you're going to get a really long answer. But we can't write all of that because all of those numbers are not significant. Your calculator will tell you exactly what you want to hear. We have to take that answer and round it to the correct number of significant figures. With multiplying and dividing, we need to report the fewest number of sig figs. That's going to be 2. So we're looking at retaining the 4 as our last retained digit. To round, you look at the 3 right next to it. It is 4 or less, so you simply drop that 3 and everything else off at the pool, and you've got 3.4 centimeters. Okay, adding significant zeros. we keep hitting these zeros. And I know by the end you're going to be like, I'm tired of zeros. I know. But we cover it a lot because the zeros can get a little tricky. And you're going to be using these rounding rules and the rules for multiplying, dividing, and we're going to cover addition and subtraction as well. You're going to be using these throughout the entire course. So please make sure that you understand the rules and you know how to apply them when you're doing multiple operations all at the same time to answer a question. Sig figs can be the difference between the correct answer and the incorrect answer when you have a multiple choice test. So that's why we're harping on it so much, because I want you to do well. And if you get the right answer on your calculator, and the only thing missing is that you didn't round it properly to the right number of sig figs, I would be really, really sad for you. I don't want to be sad. I want to celebrate. So get these sig figs right. Here we go. We're multiplying and dividing still, but we're talking about how to add significant zeros when you need to. Now, if you put into your calculator 6.0 divided by 2.00, your calculator will give you 3. It's not going to give you a decimal point with zeros after it because that calculator isn't going to give you sig figs. But you know that you took a number with 2 sig figs and divided it by a number with 3 sig figs. So your answer must have 2 significant figures. The way that you do that is by adding a significant zero. So you add a decimal point and a 0 after the 3 to show 2 significant figures. I'll give you another example. Let's say that we had 6.00 grams divided by 2.00 grams. Your calculator is still going to tell you 3. But you've got 3 sig figs and 3 sig figs for your 2 measurements. So you need to report your answer with 3 sig figs. How would you do that? You add 2 significant zeros. We'll do more practice in class, and then you'll get it. Promise, promise. All right. So here is another learning check. You've got to do these calculations and answer with the correct number of sig figs. I've got the answer on the next slide. If you want to pause it here and do it, I would encourage that, and make sure that you get the right number of sig figs. And we've also got to deal with our units. All right, here we go. First, we're going to talk about sig figs. We're going to talk about the top first. Okay, this is part 1. We're taking 5 centimeters and multiplying it by 3.408 centimeters. That's 3 sig figs and 4 sig figs. So if we were just doing that alone, our answer would have 3 sig figs. But what about the units? When we're multiplying and dividing, the same thing you do to the numbers, you're also doing to the units. If you had 2 times 2, that's equal to 4, but you could also write it as 2 squared. If you have centimeters times centimeters, it's the same thing, centimeters squared. That's why in the top, our units are centimeters squared. So if you multiply those two together and you round to 3 significant figures, you get 17.0 centimeters squared. But we've still got this other part. We've got the divided by 2.0 centimeters. Now we've got 3 sig figs and 2 sig figs. So our answer has to be rounded to 2 significant figures. You divide and you get 8.5. This is our final numerical answer. But we've still got to deal with the units. You've got centimeters squared over centimeters. If you did any kind of algebra, which if you're in this class you have, you'd know that if you had x squared over x, well, you can just cancel out one of those x's and it would simply be equal to x. It's the same thing with our units. Centimeters squared over centimeters just gives you centimeters. So that's where the units come from. Don't forget units with these problems. Again, it can cost you points. With multiplication and division, you're doing the same thing to your units as you're doing to the numbers. Now we'll do addition and subtraction. Slightly different rule. Here, what we care about is the number of decimal places the measurement has. In our example, we've got 3 different measurements. The top one has out to the thousandths place, the middle number, the hundredths place, and the third number, the tenths place. We have to report our answer with the fewest decimal places. That means the tenths place. What I like to do is line up my numbers just like you see here, and I draw a line that shows me where I have to round. So on the left side of the line, I know that's my last retained digit. Last retained digit. And the number right next to it on the opposite side of the line, that's the one I'm going to use to round. You put all these numbers in your calculator, you write out your calculator answer, and that way that line will help you see where you need to round, and then you round appropriately. So your calculator would tell you 66.102. I drew my dotted line. I know that I have to keep everything up to the tenths place, and after that it's got to go. So I've got to round. The number next to the 1 is a 0, which is 4 or less, so I just drop everything off. It's the same thing with subtraction. In the top number, we've got all the way out to the hundredths place, but in the bottom number, we've only got the tenths place. Draw that dotted line after you've lined up your numbers. Don't add any zeros. In school, you may have learned with subtraction that you fill in the zeros, right, to make it easier. Here, that's just going to throw you off because adding those zeros means that you're adding significance that you don't have. Don't do it. Do the subtraction and then do the rounding. I know that my 0 is the last retained digit, so I'm looking at the 9 to decide if I round that 0 up or just drop everything off. 9 is 5 or greater, so we're going to round that 0 up to a 1, and that's it. Again, don't feel bad if you're still like, I think I get it. We're just talking about it. You need to do some practice, and that's why it's key for you to come prepared to the live lecture, because we can hit the ground running, answer some quick questions if you have some on the front end, but usually doing practice problems will show you where your questions are, and then we take the time to answer them. All right, prefixes and equalities. Now we're getting to the good stuff. We're going to talk about the metric system here. We use prefixes in front of a unit to increase or decrease its size by a factor of 10. Some factor of 10. It doesn't have to be one factor of 10. So examples would be milligram or a microgram. You've certainly seen those if you've ever taken prescription medication, or you've taken like an ibuprofen or aspirin or something like that over the counter. You'll see something about the number of milligrams or the number of micrograms of active ingredient. mg, lowercase mg, for milligram. This funky symbol here is a mu. It's a Greek letter. You'll also see MC for micro, particularly in medicine, just because you don't want to get confused. That little tail on that M is kind of hard to see sometimes, depending on the font, people's handwriting. So using MC versus the mu is kind of handy. So there's a table, one big table, that shows all the prefixes. We're breaking it up. We're looking at prefixes, that increase the size of a unit on this slide. Okay, so we're starting with kilo down at the bottom and working our way all the way up to peta at the top. The next column is the symbol. So if you wanted to write something as a kilogram, you would put a K, which is the symbol for kilo, and then a little g, which is the symbol for gram, and that's a kilogram. Its numerical value is 1,000, and in scientific notation, it's 10 to the third. You can take these and write equalities. So 1 kilometer is equal to 1 times 10 to the third meters. That's relating two different measurements that are within the same unit system. There are also prefixes that decrease the size of a unit, starting with deci and getting smaller and smaller and smaller until we get all the way to femto. So we're talking 10 to the minus 1 all the way down to 10 to the minus 15. When we're talking about decreasing the size of a unit, let's say that you had 1 deciliter. Well, that is just a part of 1 liter, okay? That is 1/10, or 1 times 10 to the minus 1 liters. You can also say that 1 liter is equal to 10 deciliters. These are the equalities. You're going to need to be familiar with both of these parts of the table, the prefixes that increase and the prefixes that decrease. I broke them up so you can see it a little bit better, but make sure that you need to know both of those sets, all right? You need to know what the prefixes are and what they mean, particularly in scientific notation, because it'll be kind of handy when we're doing calculations. The relationship of a prefix to a unit can be expressed by replacing the prefix with its numerical value. So when you look at the kilometer, if we have that chart in front of us, we would know that kilo means 1,000. And then you just leave the meter. So 1,000 meters is the same thing as a kilometer. You can also write it in scientific notation, 10 to the third. That's also the same thing. What if we had a centigram? If you look at the table, I'll go back and show it to you. That's 0.01 or 10 to the minus 2. If we replace centi with 0.01 and then say gram, That is a centigram. In scientific notation, that's what it would look like. So you're literally looking at the prefix and replacing it with the number from that chart. So let's do some more practice here. Picometer. You find pico. That's a lot of zeros. I'm not going to write that, but I'll write it in scientific notation. And that's why I told you, knowing the scientific notation will help you a lot. So you don't have to write all those zeros. So that's the same thing as 10 to the minus 12 meters. A petaliter, we replace peta with the number 10 to the 15. Microgram, micro is 10 to the minus 6. So that is how you can look at something like a picometer or a microgram and write an equality. Because what we're saying here really is 1 picometer is equal to 10 to the minus 12 meters. 1 petaliter is 10 to the 15 liters. 1 microgram is 10 to the minus 6 grams. These are equalities. Now you might be wondering why we care about the metric system, but if you've ever looked at a nutrition label on the back of anything that you eat, you'll notice everything is in grams, milligrams, micrograms, and some for some nutrients. We don't really use the metric system on a whole as a country here in the U.S., but we do still use it for research and when we're representing daily values on nutrition labels. So you will want to know how to read those, and it may help you read those a little bit better. So ophthalmologists, which are eye doctors, they measure the diameter of the retina in centimeters. Surgeons measure the length of nerves in millimeters. They're both related to meters, right? So you can describe the same length in 2 different units. We've got 1 meter is equal to 100 centimeters. 1 meter is equal to 1,000 millimeters. Well, that means that 1 centimeter is equal to 10 millimeters. You could also say 100 centimeters is equal to 1,000 millimeters, right? But you can simplify that. That's where that comes from, okay? So we can use equalities to relate to different units. When you're dealing with health sciences, oftentimes you're dealing with small volumes. We're not dealing with liters upon liters. We're dealing with microliters oftentimes. I'm a biochemist, and in the lab, we're using pipette men, and, we're doing a milliliter is a big measurement to me, When you're dividing up that liter, you can divide it into 10 equal portions, and that's called a deciliter. You'll see deciliters a lot when you're dealing with blood. You can do the whole trick of the equalities that we did with the centimeters and the millimeters and meters to equate deciliters and milliliters. So if you have 1 liter, that's the same thing as 10 deciliters. And this you can get from the chart. You can also get from the chart that 1 liter is equal to 1,000 milliliters. So that's also from the chart. Then you take these 2 pieces, because they must also be equal, and say that 10 deciliters is equal to 1,000 milliliters. And you can simplify that down to 1 deciliter is equal to 100 milliliters just by dividing by 10 on both sides. This is an example of some of the normal values for certain substances in the blood. So if you've ever gotten blood work done and you looked at your results, then you'll definitely see things like iron and cholesterol and all sorts of things. You might see blood glucose levels. It all depends on what the test is for, and it also depends on your state. So, for example, a pregnant woman may have lower iron, and so the expected values are a little bit lower than normal, right? Versus someone who is not pregnant. Also, if you have certain illnesses, or even if you're sick, there are certain things that are reflected in your blood work that show your body is in a different state than normal. All of these values are given in ranges using these various metric units with different prefixes. So let's talk more about volume. The SI unit, we said, for volume is the cubic meter. In medicine, you'll also see the cubic centimeter, which is abbreviated CM with the 3 as a superscript, or CC, cubic centimeter. What that means is you have a cube that has a volume, or that has sides of 1 centimeter on each side. Now, again, I am not the best artiste, but I always do my best. Not too bad. What that means is we've got 1 centimeter here, 1 centimeter here, and 1 centimeter here. So 1 centimeter on each side. That's a cube that has a volume of 1 cc, or 1 centimeter cubed. That also happens to be the same volume as a milliliter. So any of these 3 things mean the same exact volume. Likewise, as I told you before, 1,000 cubic meters is equal to 1,000 milliliters, which is also 1 liter. If we're looking at the volume of a cube with 10 centimeters on each side, then you would do length times width times height, just like before. 10 centimeters times 10 centimeters times 10 centimeters would be 1,000 centimeters cubed. Remember, with your units, you're multiplying your units the same way you're multiplying the numbers. These are just visual representations. Sometimes I'm a visual creature, so this helps me. If you're used to seeing syringes, if you've worked in the medical environment, or if you've just gone to the doctors and gotten a vaccine, right? You've seen these syringes. They're usually in cc or ml. It's the same thing. So we covered volume. Now we're going to talk about mass. When you go to the doctor for your yearly wellness visit, that's what they call them now. At least when I was growing up, it was a physical, right? Now they're called wellness visits or wellness checks. You know, I have kids, and when I take them in, they're like, would you like to schedule your next wellness visit? I'm like, man, that sounds so much better than a physical. Anyway, when you go in for your wellness visit, your mass is recorded in kilograms. They'll usually tell you in pounds too what your weight is. And then if you get any kind of lab work done, you'll see grams, milligrams, micrograms, etc. Below, there's some different equalities that you might need to use if you want to convert from one unit to another to kind of make life a little bit easier for understanding some of these metrics that you're looking at. Here's a learning check where I want you to identify which one in these pairs is the larger unit. It's helpful if you have that chart, but what you need to know without the chart is what these prefixes are. So this is just the first time you're being introduced to the material. If you want to use the chart, that's fine. But know that the expectation is you'll understand what these different prefixes are without the chart. All right, which one is bigger? Millimeter or centimeter? Millimeter is 10 to the minus 3. That's what milli is. Centi is 10 to the minus 2. So centimeter is bigger. Kilogram or centigram? Kilogram, 10 to the third. Centi, we already know, is 10 to the minus 2. Which one is bigger? Kilogram. So now we're going to take the equality information and the prefixes that we just talked about and learn how to write and use conversion factors. We're going to do the writing part here, and then this will be the place where we stop. You can take a breather, and then there will be a second video where we use the equalities and conversion factors to do calculations. So we talked about equalities, we talked about the metric system, but we can also write equalities using metric and English units. Here are some examples. 1 meter is equal to 1,000 millimeters. We know that. A pound is equal to 16 ounces. 2.20 pounds is equal to 1 kilogram. This one is a US to metric equality. These top two are just definitions. And that's going to become important in a minute. Let's do some more practice. If I have 1 meter, how many centimeters do I have? You can use your chart and figure it out. I'll fill it in for you, but you'll definitely want to know how to fill in these types of questions. So 1 meter is equal to 100 centimeters. 1,000 grams is equal to 1 kilogram. We can take those equalities and write conversion factors. Conversion factors are just fractions, okay? So you take both of the numbers in your equality and you write it as a fraction. You take one number, put it in the numerator, the other number, put it in the denominator. And that's a conversion factor. Then you write the reciprocal. So each equality can be written as 2 conversion factors. You write one, you flip it over, and that's the second one. Let's do some practice. 1 meter is equal to 100 centimeters. I think we saw that before. Purposeful. You write one number as the numerator, the other number as the denominator, and for the second one, you write the reciprocal. Let's do that again. You take one number from your equality, write it as the numerator, write the second number as the denominator, and for the second conversion factor, you flip it over on its head and write the reciprocal. We'll do more practice with that in class. The numbers in any equality between 2 metric units or between 2 US system units are definitions, okay? So that's an exact number. If you've got 2 numbers in an equality that are within the same system, metric, US, they are exact numbers, which means that it's not included when counting sig figs. a definition is exact, right? So again, not used to determine sig figs. The numbers in an equality between metric and US. One number is a measurement. The other number is not. So the number obtained by measurement counts towards significant figures. Example being 2.20 pounds is equal to 1 kilogram. The 2.20 pounds is measured. So therefore, you would use it to determine significant figures. One exception is that 1 inch has been defined as 2.54 centimeters. It's an exact relationship, so you treat both the 1 and the 2.54 as exact numbers. Here are some common equalities, and you may want to print this out for your notebook, or at least, have it available. It will absolutely help you when you're doing your homework. There's metric or SI equalities, US equalities, and metric US. You can look those up on Google or something like that, but you might not get the exact same thing as your textbook. So you'll definitely want to make sure that you use what your textbook has for these equalities. Let's write some metric conversion factors. It's the same thing. You take a metric equality, which you can get from your chart, and you write fractions. Both of them are conversion factors. It's just the inverse, so it's exactly the same. And both of these numbers are exact numbers, so you don't have to include it for your sig figs. We can also write metric US conversion factors, but remember, unless we're talking about 1 inch is equal to 2.54 centimeters, you're going to have a number that is measured and counts towards your significant figures. I want you to write conversion factors from the equality for each of the following. We've got liters and milliliters, and then meters and inches, okay? Liters to milliliters. Now you may be able to find some of these directly on the chart. For example, 1 liter is equal to 1,000 milliliters. Then we've got meters and inches. That's here. You may encounter equalities that are not on the chart specifically, and you may have to take 2 equalities and relate them to get the equality that you need. We did a couple of examples of that earlier in this lecture video, and we'll do some more of that in class. Now these are the answers. So I already circled where you got these equalities from. And then you just write the equality as a fraction. You take one number, put it in the numerator, the other number, put it in the denominator, and then you flip it for the reciprocal. An equality may also be given to you within a problem, and it only applies to that problem. An example might be the car was traveling at a speed of 85 kilometers per hour. Well, the equality is in 1 hour, you are moving a distance of 85 kilometers. You can write conversion factors, like here. The 85 is measured. It's got 2 significant figures. So if you were using that to do a calculation, you'd have to use those 2 significant figures towards figuring out how many sig figs your answer should have. The 1 hour is exact. Let's say you were doing a problem and you're talking about the price of onions. It's $1.24 per pound, which is, for this state, that's about right. You might get some of the cheapos for maybe 99 cents a pound, but $1.24 is probably like those huge red onions that you can get. That is an equality. 1 pound is equal to $1.24. That $1.24 is measured. It's got 3 sig figs. That will be used to figure out how many sig figs your answer needs at the end. We can also use conversion factors when we're figuring out dosages. So for a medication, you get a specific number of milligrams per kilogram of body weight. That's usually how it's done. You can also figure out, okay, each capsule of this particular antibiotic has this many milligrams of active ingredient. And from there, you can figure out how many capsules you need based on the person's body weight. In this case, if we have 1 capsule is equal to 250 milligrams, the 250 milligrams is measured. It's got 2 sig figs. That 0 is a placeholder. The 1 capsule is exact. So those 2 sig figs would count towards the sig figs when you're doing your calculations and figuring out how many sig figs your answer needs. Percentages, parts per million, parts per billion, those things also are conversion factors. A percentage is written as a conversion factor by choosing a unit and expressing that numerical relationship in 100 parts of the whole. So if you have 18% body fat by mass, then that means that you've got, say, 18 grams of body fat for every 100 grams of body, okay, of your person. That is a conversion factor. We can also use parts per million or parts per billion. You'll see that more when you're looking at like water safety, where they'll report different toxins and things that you don't want in your water. There's supposed to be, this much or less in your drinking water. And we're talking parts per million, parts per billion, which is milligrams per kilogram, micrograms per kilogram. So it's very, very, very small amounts of these things. One example would be benzene in your water. You're supposed to have a certain number of parts per million or less. So that's where these ratios come in handy. Let's do a learning check. Write the equality and its corresponding conversion factors, and then identify each number as exact or measured and give it significant figures, right? Salmon contains 1.9% omega-3 fatty acids. 1.9%. We can write that percentage as a conversion factor. We can write 1.9 grams, let's say, of omega-3 fatty acids. FA is my abbreviation for that. Out of every 100 grams of salmon. We know that percent means part out of a whole, and that whole is 100, right? 100 parts is the whole. So if we say 1.9 grams, which makes sense, because we're talking about something with mass, right? Salmon. 1.9 grams of omega-3 fatty acids for every 100 grams of salmon. And we can use that to do calculations. Let's say that we had a piece of salmon that was I don't know, 1.2 kilograms, which is kind of big piece, right? Maybe it's a small fish. You can calculate how many grams of omega-3 fatty acid you have based on your conversion factor. But we're not going to do that this time. That's for next time. So make sure that you tune in to the second part. Thanks for watching. Again, make sure to watch the next video that's going to cover the remaining sections of Chapter 2, where we're taking all of this information about equalities, measured numbers, significant figures, and writing conversion factors, putting them to work, doing problems. Also, make sure that you come to the live lecture, or at least tune in and watch it on YouTube. Do the practice problems, participate. You'll also get details about assignments that are coming up and exams. Thanks for watching. Be safe.